So how do we tell things apart in a world of pure abstraction? I mean, seriously, think about it. If you have a space with no rulers, no coordinates, just a bunch of points floating around, how can you possibly say, this point is different from that one? It's a huge question, and it gets right to the heart of what space even means.
Well, that's exactly what we're going to tackle today. We're going on a journey. We're going to climb what's known as the ladder of separation. Now, this comes from a wild field of math called topology. You can think of topology as the study of shapes and spaces, but, and this is the crazy part, without caring about distance or angles. And with each step we take up this ladder, we're going to get more and more power to tell things apart. We're going to go from a total blurry mess to something crystal clear. Because, in topology, not all spaces are created equal. Some are just incredibly fuzzy. Points just kind of blend into each other, like a poorly focused photograph. But others, they're sharp, they're defined, way more like the world we live in. And the secret sauce, the thing that gives a space its sharpness, it's these rules, these separation axioms.
All right, so this chart right here, this is our roadmap. It's our ladder. Now you'll see it has labels in both English and Arabic, but we're going to stick with the English terms for this walkthrough. We're starting at the very bottom at what's called T0, and we're going to climb our way up. And just remember, every single level adds a stricter rule, a brand new tool to our toolkit, and makes the space just a little more well-behaved. You ready? Let's get climbing. All right, first up, the first distinction. We're looking at T0 and T1. This is like the baby step. It's how we go from a space where points are maybe completely indistinguishable to one where we can, at the very least, say, hey, those two things are not the same. So let's start with T0, the Kolmogorov axiom. Here's the deal. It's super simple. If you've got two different points, say A and B, all this rule says is that there has to be some kind of neighborhood. Just picture a fuzzy bubble around one of them that contains A but not B, or vice versa. It's just a one-way street, But hey, it's a start. It's the bare minimum to say, okay, these 2 points are definitely different.
But okay, that was T0. The real upgrade comes with T1, the Frechet axiom. Remember how T0 was kind of one-sided? Well, T1 introduces symmetry. Now, for our 2 points A and B, you can find a neighborhood around A that doesn't contain B, and you can find a neighborhood around B that doesn't contain A. See the difference? Now, each point can be isolated from the other. It's a two-way street.
And this simple little rule has a huge result. In a T1 space, every single individual point, what mathematicians call a singleton, is now a closed set. What does that mean? Well, think of a closed set as something that has its own solid boundary. It's not leaky. This sounds super abstract, I know, but trust me, it's a massive deal. It means a single point is no longer just some part of a fuzzy blob. No, it has its own solid mathematical identity.
Okay, so we've got solid points. Where do we go from here? We climb higher. Our next stop is T2, also known as the Hausdorff space. And you're going to want to pay attention here, because this is a major milestone. This is the point where these abstract spaces start to feel, well, normal. They start to behave like the space we actually live and breathe in.
So think back to T1. We could find a bubble around A that misses B, and another bubble around B that misses A, right? But what if those two bubbles overlap in the middle? They still could, right? There's no guarantee they're separate. To truly separate them, we need to build a fence between them, make sure there's no way they can touch. So how do we do that?
And the answer is the T2 axiom. It's so elegant. For any two distinct points, you can find two neighborhoods, one for each point, that are completely separate. They don't overlap at all. They're what we call disjoint. It's literally like giving each point its own private bubble, its own personal space. That is what real separation looks like.
Okay, but why is this such a game changer? Here's why. In a Hausdorff space, if you have a sequence of points that's heading somewhere, converging, it can only converge to one single unique limit. Just one. This is exactly how we think the world should work, right? A rocket flying to the moon doesn't also land on Mars at the same time. This idea, unique limits, is so incredibly important that it's basically the standard for almost all of calculus and analysis.
All right, pretty cool. We've mastered separating one point from another point. But let's be real, the universe isn't just made of lonely individual points. What about more complicated stuff? What if we need to separate a single point from a whole crowd of points? Or even separate two different crowds from each other? Time to climb higher.
And that brings us to the T3 axiom, which defines what's called a regular space. This rule gives us a new superpower. We can now take any single point and any closed set, remember that's like a well-defined group, as long as the point isn't in it, and we can draw two completely separate, non-overlapping bubbles around them. We can now officially put a fence between one person and an entire crowd.
And for today, the top of our ladder is the T4 axiom, which gives us a normal space. This one is even more powerful. Now we can take any two separate closed sets, so two separate crowds, and put non-overlapping bubbles around both of them. No problem. This property is so incredibly strong that it unlocks some really famous and deep results in math, like something called Urysohn's lemma. And what that lemma does, basically, is it gives mathematicians a way to build smooth bridges, or functions, between these separate sets. It's a huge deal.
Wow, okay, that was a pretty fast climb from T0 all the way up to T4. Let's just pause for a second and take a look back down the ladder with a quick cheat sheet.
So let's run through it one more time. We started at the bottom with T0, just getting a basic distinction. Then we climbed to T1, which made our point solid and closed. The really big jump was to T2, Hausdorff, giving us those all-important unique limits that feel so natural. And then we finished our climb with T3 and T4, leveling up our powers to separate not just points, but a point from a set, and even two whole sets from each other. Every single step up this ladder gave us more structure and way more clarity.
And you know, at the end of the day, these axioms, they're not just some random rules for a math class. They are the fundamental toolkit. This is what mathematicians use to define what it means for something to be continuous, to prove really deep things about the universe, and to truly understand the properties of shapes, no matter how weird or high-dimensional they are. So it really leaves you with a big question, right? Now that we have this incredible toolkit for defining space so precisely, what kind of amazing new worlds and structures can we build and explore next?